In this video, we're going to take a look at some of the properties of logarithms. We saw some of the properties in the previous video, but we'll take a look at three new properties in addition to those that we had already seen. Working with these properties is a preparation for solving logarithmic equations. These properties will allow us to rewrite logarithmic expressions in a way that will allow us to get started on solving the equations. Our objectives in this section are to work with the properties of logarithms, to write a logarithmic expression as a sum or difference of logarithms, to write a logarithmic expression as a single logarithm, and to evaluate logarithms whose base is neither 10 nor e. And then the last objective is to graph logarithmic functions whose base is neither 10 nor e with a graphing calculator. We did some of the graphing by hand in the previous section. Here we'll talk about how to graph those with a calculator. So let's take a look at these properties. Like I said, the first two on our list here we saw in the previous section, but just to review, remember that the log base a of a we can think of as the exponent I put on a to get a, and that's 1, and that's a simple proof because a to the 1 gives me a. So the exponent we're looking for is 1. And the second one is, remember, the exponent we put on a to get 1 is 0 because a to the 0 is 1. So those two have fairly simple proofs. The third and fourth and fifth properties on this list are new, and their proofs are a little more complicated. So let's take a look at them. The property 3 here, we want to show that log base b of a product is the same as the logarithm of the first factor plus the logarithm of the second factor. That's what we want to show. So what we're going to do is put some letters on these expressions. So let's say let's use s and t maybe. Let s be the log base b of x, and let t be the log base b of y. And then what we want to do is think about how to rewrite those equations in an exponential form. So what we would have would be the base b with the exponent s would give us x, and the base b with the exponent t would give us y. And what we're interested in is finding out what exponent we put on b to get that product of x times y. So if we look at x times y, that would be b to the s times b to the t. And if you think about how the properties of exponents work, we could rewrite that as the expression with a single base b to the s plus t. So we would add the exponents. So that's telling us that the log base b of x times y, the exponent we put on b to get x times y, is s plus t, and that is the same as the log base b of x plus the log base b of y. If you look above, right, s was defined to be the log base b of x, and t was defined to be the log base b of y. So we have what we want. The log base b of the product is the sum of the logarithms of each factor. So it's connected to exponent rules, right? If we have a product with the same base, we add the exponents to get the exponent overall. proof of the fourth property is going to be very similar. We'll say let S be the log base b of x and t be the log base b of y. Then we want to look at the difference of the logarithms this time. Log base b of x minus log base b of y would be, sorry, let's go back up to this line. So we've got up above is that b to the s is t again, or is x, and b to the t is y. Right. I'm going to erase what I just did in this step. I wasn't thinking carefully. Sorry about that. So then we want to know about the quotient, right? So we want to look at what would x divided by y look like. X divided by y would be b to the s divided by b to the t, because x is the same as b to the s and y is the same as b to the t. And that's the same thing as b to the s minus t. Remember, when you have a quotient of factors or of expressions with the same base, you can rewrite it as the base raised to the difference of the exponents. And that tells us then that the exponent we put on b to get x over y is the same as s minus t. So the log base b of x divided by y, the quotient, is the same as s minus t, but s was what we used to represent the log base b of x, and t was what we used to represent the log base b of y. So we have what we wanted to prove. The log base b of this quotient is the log base b of the numerator minus the log base b of the denominator. Then property 5, let's go through the proof of that one. We're wanting just to know about if I have x raised to a power, what is the logarithm of the base b for that expression compared to the log base b of just the original x. So we're going to do we'll say s again be log base b of x. Then, rewriting it in exponential form, b to the s would give us x. Right? And then if we have x to the r, that would be b to the s raised to the r. But when you have a power of a power, you can take the product of the exponents. So that tells us that the log base b of x to the r, which is what we're wondering about, would be s times r, because the exponent we put on b to get x to the r is just sr, but s was just the log base b of x, so we have r times the log base b of x. And that's what we were trying to show. The log base b of x to the r is the same as r times the log base b of x. I'm not ever going to ask you to prove these properties, but I did think it was important to go through the proofs just that you could see that they're not just coming out of nowhere. So again, they mostly rely on the properties of exponents that say when you have a product, you add the exponents. When you have a quotient, you subtract the exponents. And when you have a power of a power, you multiply the exponents. So what's going to happen next is we're going to try to use these properties to either take something that's a single logarithm with a complicated input and expand it into the sum or difference of logarithms with simpler inputs, or we're going to take logarithms that are, sums or differences of logarithms and try to combine them into a single logarithm. So, in our first example, we have logarithms that don't involve any variables, so we should be able to come up with a single value for each of these expressions. Notice on the first one, it's asking us to do log base 2 of 160 minus log base 2 of 5. So we have these properties. The first one says that log base b of a product is the log base b of the first factor plus the log base b of the second factor. I'm just rewriting them so we can see them on the same screen here. The second one says that log base b of a quotient is the log base b of the numerator minus the log base b of the denominator. And then the third one says that the log base b of x raised to a power is that power times the log base b of x. So this looks like the right-hand side of property 4. We have a difference of logarithms, so we want to combine them into one, do a single logarithm of the same base. So we could say log base 2 of 160 divided by 5. And then we'll simplify 160 divided by 5, that should be 32. So log base 2 of 32, and that's a value we know. We're thinking, what's the exponent? We put on 2 to get 32, and we need 5 factors of 2 multiplied together to give us 32. So we were looking at this and thinking, okay, it looks like a difference of 2 logarithms. How can I simplify that? I can put it together as 1 with the same base, simplify that quotient, and then go from there. All right, moving on to example 1b here. If we think about what this looks like, it looks like, well, I've got 8 raised to a power, so this looks like log base b of x to the r, that kind of form. So what I can do with that is rewrite it as move the exponent down, so 33 in this case times the log base 2 of 8. Well, I know what the log base 2 of 8 is, that's 3. So we have 33 times 3, so this would be 99. So we used property 5 to move the exponent 33 in front of the logarithmic expression, evaluate this logarithm. The exponent we put on 2 to get 8 is 3, so we have 33 times 3. Then example 1c, this exponent we can see appears to be like the right-hand side of property 3. We have a sum of 2 logarithms, so we're going to leave this base 3 alone for now. Rewrite the exponent as a single logarithm, log base 3 of 5 times 2, which would be 10. So we have 3 to the log base 3 of 10. Now I don't know what the log base 3 of 10 is, but we had in the previous section b raised to the log base b of x gives us x. So this is one of the properties from a previous section that says if I have a composition of a function and its inverse, which we have here, the exponential function with base 3 and the logarithmic function with base 3, those are composed. If I compose a function and its inverse, I get the input back, which is just 10 in this case. So that property applies here and should just give us 10. So example C required 2 properties. First, the property that it allowed us to combine the exponent logarithms, and then the property that says a function and its inverse composed, we just get the original input back. Okay, moving on to example 2. Now we have, you can see, single logarithms that we're trying to expand so that we have simpler inputs, but maybe a sum or difference of logarithms. So, again, I'm going to rewrite those properties over here. First one is like that. Log base b of a quotient is the log base b of the numerator minus the log base b of the denominator. And the log base b of x to a power is that power times the log base b of x. So those are our properties that we're trying to use here to expand the expressions. So on example 2a, you can see that the input is a product, and then that one of the factors has an exponent that's not just 1. So we're going to be able to use first property 3 and then property 5. So if we use property 3 first, this would be log base 7 of the first factor plus log base 7 of the second factor, which is y. So that's using property 3. And then if any of these inputs has an exponent, we want to move that exponent down to keep the input as simple as we can. So now we want to use property 5 on the first term. So we'd have 2 times the log base 7 of x plus the log base 7 of y. And now we know this is as simplified as it can get because each of the inputs is just a single factor with exponent 1. So x and y for the inputs. On the next one, first you want to remember that the cube root is the same as a power 1/3. So we can rewrite this not using properties of logarithms, just using that idea that we can rewrite a radical as an exponent. And that exponent, the 1/3, applies to the whole input, whereas the exponent 2 applies only to the factor of y. So what we could do is first use property 5 to move that exponent 1/3 in front of the whole group. And then we could use property 3 to break up the product, but the 1/3 needs to be times the whole thing. So we would want to put parentheses like that. 1/3 times the log base 5 of x plus log base 5 of y squared, 1/3 times that whole group. And then finally, we'll use property 5 one more time because we don't want the input to be y squared on the second term. So we could have 1/3 times the log base 5 of x plus 2 times the log base 5 of y. So that's again using property 5, and then if we want to, we could expand that or distribute the 1/3. 1/3 log base 5 of x plus 2 times 1/3, so 2/3 times the log base 5 of y. And if you can do a couple of those steps at once correctly, that's fine with me. So if you had a different way of getting to this answer, but as long as you're getting to exactly the same thing, that's fine. All right, then the next one, we can see we have a quotient, and in the denominator we have again a radical, which we can rewrite as an exponent. So let's do that first. So let's just first rewrite the exponent instead of the radical. So 2 minus x to the 1/5 in the denominator. And then right away we've got quotient, so we'll use property 4 this time. Log base 4 of the numerator minus log base 4 of the denominator. And then we can use property 5 to move the exponent off of the second term here. So we have log base 4 of x minus 1/5 times the log base 4 of 2 minus x. So notice on this one, the input for that second term is now 2 minus x. But we don't have anything that allows us to rewrite a logarithm of a difference. We've got something that allows us to rewrite the logarithm of a product, the logarithm of a quotient, or the logarithm of a power. But notice there's nothing we can do to simplify this logarithm of a difference. If we had a difference of logarithms, that's a different thing. But here we have a logarithm and then the inputs are subtracted. So there's nothing we can do to simplify this any further. So we're done with that. Realize I didn't manage my space here very well. So let's move down here, for example, D. This one looks complicated. We've got the log base b of the square root of x times the square root of y times the square root of z, and it's all these nested square roots. Let's work first on just getting that written in exponential form. So we'd have this would be equal to the log base b, and we've got, I'm going to write this first, z to the 1/2, and then we've got y multiplied with that raised to the 1/2, and then we've got x multiplied with all that stuff also raised to the 1/2. So we can see that z has actually 3 square roots over it. X only has 1 square root, so we'd have x to the 1/2. Y has 2 square roots, which would be to the 1/2 and then to another power of 1/2, so y would be to the 1/4. And then z has 3 square roots over it, so that would be to the 1/2 times 1/2 times 1/2, which would be, z to the 1/8. So rewriting that inside expression and using properties of exponents, we've got log base b of x to the 1/2 times y to the 1/4 times z to the 1/8. Then we can use property 3, I guess. We got 3 factors this time instead of 2, but that's fine. We can do log base b of the first factor plus log base b of the second factor plus log base b of the third factor. So this property can be expanded to involve as many factors as we have. So we can just split it up as the sum of the logarithms of each factor. And then we'll use property 5 to move the exponents. So we'll have 1/2 times the log base b of x plus 1/4 times the log base b of y plus 1/8 times the log base b of z. And kind of complicated, especially at the start, but once we had it sorted out and written in a nice way with exponents, then we were able to go from there. After that one example, e probably won't seem so bad. Again, let's first rewrite the radical as an exponent, and this time there's just an x inside that radical. So not using a property of logarithms, just rewriting that radical. We've we've got this. So that's going to be log base 5 of the numerator minus log base 5 of the denominator. So using property 4 first, then you can see that on the first term here we can move the exponent down. And in the second term here, we can't move the exponent yet because it only applies to the y. So first we need to break up this product. And we need to be careful that we put parentheses around this group because we want to subtract that whole expression. So we can split this logarithm of a product up into the sum of the logarithms of the factors, but we were supposed to subtract that whole logarithm, so we need to subtract both terms of this sum. So we'll have 1/3 times the log base 5 of x minus, we can move this 2 down, 2 times the log base 5 of y, and then minus from distributing here the log base 5 of z. So let's see, we used property 3 on this line and then property 5 on that line. Actually, we used 5 and 3 in the second line. Okay. One thing to mention on this one, notice that any of the factors that were in the denominator end up with a minus in front of them when we expand. So the y term has a minus and the z term, that logarithm has a minus in front of it, and any of them that are in the numerator have a positive coefficient. So you can always double check that at the end, that anything that had been in the denominator should have a negative in front of it once you're done. Anything that had been in the numerator should have a positive coefficient in front of it when you're done. And then we want to go the other direction. And this is actually the direction we'll mainly be using when we're trying to solve logarithmic equations. We're typically trying to get a single logarithm instead of a sum or difference of logarithms. So I'll write those properties one more time. And as silly as it seems for me to be rewriting these every time, I highly recommend that you do the same thing. Write them several times until you get to the point where you can write them and you know that you're not having to look at a piece of paper to make sure you got it right. This notation is new and it's, can seem unfamiliar, and then these properties kind of start to look the same and it's easy to get confused about, oh, which way did it go? You need to make sure you have them down very solidly when you're ready to take a test. So make sure that you can write them and be confident in how you're writing them so that you can use them then and kind of look at what you've got when you're trying to rewrite examples like these. So log base 4 of 7 plus log base 4 of 9, it looks like that's a property 3 form. And we're trying to take the two that are added and put them back to 1. So we'd say the log base 4 of the product of these two, 7 times 9, so 63. And I don't know what the exponent I'd put on 4 to get 63 is. That's not an integer value, so we'll just leave it like that. And the next one, we've got something that looks like property 4. So we'll use that property. We've got a difference, so we want to put that back together as the logarithm of the same base. And the first one would go in the numerator and then the second one in the denominator. So the log base 7 of 14 divided by x. Make sure that you have a single logarithm here, not log base 7 of 14 divided by log base 7 of x. That's something different. So you want a single logarithm and then the input 14 divided by x. The next one, notice this 2 is kind of in our way. We need to move this 2 out of the way before we can combine these into one logarithm. So first we'd want to use property 5 to move that to 2. So we now have a difference of logarithms with no coefficients in front. So always move the coefficients out of the way first, and then we can use property 4 to combine them. So we'll have the log base 9 of 6 divided by y squared. And we're done because we got it into a single logarithm. Alright, now we've got some natural logs, but remember that's just log base e, so the same properties all apply here. And again, we've got this 2 that we need to move first. We can rewrite that as natural log of c squared. So we used property 5 first, and then the next thing I'm going to do isn't necessary, but it helps to avoid any confusion. I'm going to write everything that's a plus first, and then write the things that are subtracted. So I'm going to just rearrange, so I'm not using any properties of logarithms, but I'm going to do that so that I don't get confused about the order, right? So I want to add this and then subtract the natural log of c squared. So I'm going to use first my property that says I can put the sum of these two logarithms together as the logarithm of the product, a plus b times a minus b. So there I used what, property 3, where I took a sum of logarithms and wrote it as the logarithm of the product. And then I'm going to use property 4 because now I have a difference. And I'll take the numerator from the first term and the denominator from the second. So if I want to, I could multiply a plus b and a minus b to get a squared minus b squared. Probably looks a little better that way. But that's not using a property of logarithms, that's just multiplying and foiling to get a squared minus b squared. Alright, then example E here. There are different ways to approach this. The order doesn't really matter as long as you get the same thing at the end. I guess I'm going to distribute this 3 first thing, so I'm just going to distribute that, so I'll have 3 times the log base 3 of x plus 6 times the log base 3 of y. So I didn't use any properties of logarithms there, I just distributed the 3, and now I'll move these coefficients up and put them as exponents. So I'll use property 5 twice. And then I'll use property 3 because I have a sum to put those back together as 1. And we're done because now we've got a single logarithm. You want to make sure that you're keeping track of the base. It's so easy to just be so focused on these properties and how the inputs are related that you forget to track that base. So always double check that the base you started with still is written at the end. Right, so we want to make sure we still have the base 3 hanging around and the end of the problem. Also, make sure that as you're writing these, those bases are subscripts. You don't want it to look like the base is even with a logarithm and then the other stuff is an exponent. You want to make sure that those bases look like subscripts for the logarithm and that the inputs are on the same level as the logarithm. Alright, then the last one of this type of example, We want to, again, let's see, move the coefficients out of the way and put them up as exponents. And I'm going to rewrite x to the 1/2 right away as square root of x. The second term here doesn't have any coefficients, so we don't need to move anything. And then the last one will have log base 5 of 2x minus 1 raised to the 3rd power. And again, I'm going to reorder these so that the ones that have positive coefficients are first. And then the last one would be the log base 5 of x plus 1. Combine the first two into a product. So first we used property 5, then we reordered, and then we're using property 3. So we'll have log base 5 of square root of x times 2x minus 1 cubed. And then we'll use property 4 to combine the difference into a quotient, or a logarithm of a quotient. And then we're done. So again, this is the type of thing we're going to be using extensively when we start solving logarithmic equations, trying to take a sum or difference of logarithms and combine it into a single logarithm. All right, then this next one is kind of a different type of example, but I think will help solidify how we can use these properties in different ways. So again, I'm going to rewrite these. Log base b of a product is the log base b of the first factor plus the log base b of the second factor. Oops. Log base b of a quotient is the log base b of the numerator minus the log base b of the denominator. And the log base b of x to a power is that power times the log base b of x. And again, if you can even just say those things as you're writing them, say them in your head, say them out loud, whatever, that I think will help them stick a little better as well. So what we're told here is that the natural log of 5 is a, and the natural log of 7 is b. So what we want to be able to do is connect what's given to 5 and 7, and this is not a great example. So let's, instead of natural log of 10, which isn't related to 5 and 7, let's do, I don't know, the natural log of just 35 instead. So 35 is the product of 5 and 7. For emphasis, we could rewrite that, and that would be the same as the natural log of 5 plus the natural log of 7, and that would be a plus b. So the natural log of 35 would be, in terms of a and b, it would just be a plus b. So there shouldn't be any natural logs left in your answer here. In the next one, we want to relate 125 and 49 to 5 and 7. Well, we can think, well, 125 is 5 cubed, and 49 is 7 squared. And then use the properties of logarithms. We'd have then the difference, natural log of 5 cubed minus the natural log of 7 squared. And then we can use that last property that allows us to move these exponents. So 3 times natural log of 5 minus 2 times the natural log of 7. Natural log of 5 is a, and natural log of 7 is b. So we've got 3a minus 2b. And again, there aren't any natural logs left in our answer, just a's and b's and then some other coefficients. In example C, we want to think, how is 0.2 related to 7 or 5? 0.2 is the same as 2/10, which is the same then as 1/5. So we could think, well, that's the natural log of, either write it as 5 to the negative 1 or natural log of 1 minus natural log of 5. Either way is fine. Natural log of 1 is 0 because e to the 0 is 1. Right? And then natural log of 5, that's what was defined to be a. 0 minus a is negative a. So the natural log of 0.2 would be the opposite of a. Then the natural log of the fourth root of 35, that would be the natural log of 7 times 5 is how 35 is related to 7 times 5, all to the power of 1/4. So we could move that exponent and make it a coefficient, so 1/4 times the natural log of 7 times 5, and then break that up as the natural log of 7 plus the natural log of 5, and then we want to make sure that we put parentheses around that because we want 1/4 times the whole thing. So we'd have 1/4 times b plus a, so we get 1/4 times b plus 1/4 times a, and the order doesn't matter there. You could have a first or b first. You want to make sure that each of them is multiplied by 1/4 and that they're added together. So again, we're trying to relate the inputs to the numbers that were given, so to 5 and 7 in this case. Now we get to one of the most important formulas we're going to be using for logarithms, and this is the formula that's going to allow us to evaluate logarithms on our calculator that are not base e or base 10. One of the tricky things about this formula is that we're not going to be using it over and over in other sections. It's kind of just here and it's fairly isolated, but it's an important formula to remember. So it's called the change of base formula, and you can see what it says is this: the log base b of a is the same as the log base c of a divided by the log base c of b. So we can change from a base that's given to any other base we choose as long as they're positive numbers and not equal to 1. So remember, the bases are always positive and not 1. So if base 3 is given, we can switch to base 5 if we want to. And so what we do is notice that the input for the numerator logarithm is the same as the input for the original logarithm. The input for the denominator logarithm is the base of the original logarithm. And then the new base is whatever you want it to be, but it has to be the same in the numerator and the denominator. So the way this is useful is if we choose the base we're switching to be 10 or e, because that has a button on our calculator. So if log base b of a is given, if we want to evaluate it on our calculator, we can do log base 10 of the input a divided by log base 10 of the original base b, or we can do log base e of the input a divided by log base e of the original base b. So here's how we're going to use this. If I want to know what log base 3 of 10 is, I'm wanting to know what exponent do I put on 3 to get 10. And I don't know what that is without a calculator, because I know 3 squared is 9 and 3 to the third would be 27. So I can say, well, I know it's between 2 and 3 somewhere, but I don't know any better than that, really. So on a calculator, I could do log base 10 of 10 divided by log base 10 of 3. And I can get that, or if I prefer, I can do natural log of 10 divided by natural log of 3. Either one is fine. Let's grab our calculator. So we'll do first, just so we can see that they're actually the same thing, log 10. That one we actually know, that would just be 1, right? Divided by log 3. So that gives us about 2.096 roughly. And let's just look at the other one to see that they're the same. Also 2.096 roughly. Right? So it doesn't matter which one we do. This isn't saying that the log of 10 is the same as the natural log of 10, or that the log of 3 is the same as the natural log of 3. Those values are all going to be different, but their ratios are the same, and they're both equal to the log base 3 of 10. So what we're finding is we should see 3 to the 2.096 is roughly 10. Let's check that just to make sure. It's not going to be exactly 10 because we rounded, but it's going to be pretty close. Okay. And then similarly, log base 7 of 3. Using that change of base formula, we can do log of 3 divided by log of 7. Or we can do a natural log of 3 divided by natural log of 7. They should give us the same thing. And let's think about what we're expecting. 7 to what gives us 3? We know that 7 to the 0 is 1, and 7 to the 1 is 7. So this should be somewhere between 0 and 1. Let's check and see. Log 3 divided by log 7 is 0.565 if we round to the nearest thousandth. And if you want to double check the other one, it's going to be the same. Natural log 3 divided by natural log of 7. Also 0.565 roughly. So then 7 to the 0.565, we're expecting something close to 3. Yep, looks good. Alright, and then the next one, saying without a calculator, evaluate log base 2 of 7 divided by, or times log base 7 of 8. I don't know what log base 2 of 7 is. I don't know what log base 7 of 8 is. But I can say, well, I know that that's the same as log of 7 divided by log 2, so the first one switching to base 10, times log of 8 divided by log 7. So we've got these two fractions multiplied together. I see that I've got matching factors in the numerator and denominator. So now I can switch that back to log 8 divided by log 2. And again, I don't know what the log base 10 of 8 is. I don't know what the log base 10 of 2 is. But now I can use the change of base formula in the other direction. If I have a quotient like this, I can put it into the log base 2 of 8. And that's something I know. The exponent I put on 2 to get 8 is 3. So this was by the change of base. And this was by the change of base. So using it opposite directions, we were able to evaluate that expression that we couldn't evaluate by doing each factor individually, but we could evaluate by doing some rewriting and getting to something we knew. All right, so then we've got an example where we want to solve an equation using our graphing calculator, but one side of the equation has the log base 4 of x plus 2, and there's not, at least on my calculator, there's not a way to punch in log base 4 of something. So I want to do something like maybe y1 equals log base 10 of x plus 2 divided by log base 10 of 4. Use change of base formula. So that since there's not a button for log base 4 of x plus 2, we can do just this, or we can do natural log of x plus 2 divided by natural log of 4, either one. And then y2 equals x plus 7, and find intersection points. So let's go ahead and graph those. So log of x plus 2 divided by log 4 is one of them, and then x plus 7, that's the other. Let's just do a zoom standard for now. Alright, so what you can see from this picture is that those don't actually intersect. So I'm going to copy that. This linear function, the x plus 7, is always going to be growing more quickly than this logarithmic function. So the logarithmic function is always going to, it's not going to grow quickly enough to catch up with that line x plus 7. So there are no intersection points. So there's no solution. Right, so the key was to be able to switch using the change of base formula to be able to graph the log base 4 of x plus 2. And then once we had those graphs, we saw, wait, there's not even any intersection points, so no solution. So usually there will be solutions to these equations, but every once in a while they'll throw in an example where there aren't any, and that's how you see that. There's no intersection points. All right. And then just a couple more examples getting used to using these properties to do different things. So example 8 is asking us to express y as a function of x. So basically it's asking us to try to solve for y. And we can see we've got all sorts of natural logs here. What we want to do is try to combine as many of them as we can. So let's do this. First let's move this 2. So we've got natural log of y squared. Maybe we're not even going to want to move that to 2. Let's hold off on that one. Let's leave that as just 2 times the natural log of y. But on the other side, let's combine these as much as we can. First we want to move the coefficients. So we've got natural log of x to the negative 1/2 plus natural log of x squared plus 1 to the 1/3 plus natural log of c. So we've got natural log of, these are all added together, so we've got x to the negative 1/2 times cube root of x squared plus 1 times c. And that's 2 times the natural log of y. Alright, so then we've got, let's rewrite this side one more time as cube root of x squared plus 1 times c, and then put the x to the negative 1/2 as divided by the square root of x instead. And yeah, let's go ahead and move that to 2 up. So we'll have natural log of y squared equals the natural log of this mess. If the natural log of one side is the same as the natural log of the other side, we know then we're not dividing by the natural logs, but they have to have the same inputs if the natural logs are the same. So that would imply that y squared has to be the cube root of x squared plus 1 times c divided by the square root of x. Which means that y would either be positive or negative square root of cube root of x squared plus 1 times c, all divided by square root of x. That's quite a mess. That's okay to leave it like that. Another thing you can notice though is that, let's see, we've got, I'm going to rewrite this as positive or negative. We've got the c that's just inside of a square root. X squared plus 1 is inside of a cube root and a square root. So we could do that. And this x in the denominator is under 2 square roots. So we could probably do a little better here. C is just a constant, and if we take its square root, that's still just a constant. And then the positive or negative, if we just put like maybe a d that we allow it to be any sign, then we could have x squared plus 1 to the 1/6. We would multiply those exponents, and x to the 1/4 in the denominator. That looks a little less messy. But again, where we left it right here is fine, but we could make it look a little bit cleaner where we let d be any value. Finally, we're trying to show that the natural log of the square root of x plus the square root of x minus 1 added to the natural log of the square root of x minus the square root of x minus 1 is 0. So we want to work with the left-hand side and do some rewriting and try to somehow show that that's actually 0. So the left-hand side, natural log of the square root of x plus the square root of x minus 1 plus natural log of the square root of x minus the square root of x minus 1. We can use property 3 because we have the natural log, the sum of two natural logs. We can put it together as 1, and this is going to look like a mess at first. That times square root of x minus square root of x minus 1. And then if we FOIL this out, we have like an a plus b times an a minus b pattern. So we would have the natural log of a squared, which would just be x, and then minus b squared, which would be x minus 1. Where in this case a is the square root of x and b is square root of x minus 1. So we're just using that pattern. So we've got the natural log of x minus x, and then that would be plus 1. So that's just the natural log of 1, and that's 0 because the exponent we put on e to get 1 is 0. And that's what we were trying to show. So it was a little bit messy, but using properties of logarithms and then expanding this product, we were able to get down to the natural log of 1, and that's just 0. Alright, so like I said, in the next video where we're solving logarithmic equations, this stuff will seem more useful maybe than it did here. Here it tends to seem just like an exercise in rewriting things. In the next video, you're going to see a purpose to this.